Welcome back to the ChemDoctor, and this is the second video in the playlist in the Le Chatelier's principal videos that deals with temperature effects. So the first video in this area dealt with an exothermic reaction, and in this presentation what we're going to do is look at an endothermic reaction. So in this case, the model reaction is the decomposition, if you will, of SO3 into SO2 and oxygen. And we see that the delta H for this reaction is 197 kilojoules per mole. So since our delta H is a positive number, this is an endothermic reaction. And there's a couple of things I want to point out before we get to the meat of the matter here. And the first is, remember that this is a thermochemical equation the way it's written. So what that means is that when we decompose exactly 2 moles of SO3 to form 2 moles of SO2 and 1 mole of oxygen, then that transition requires exactly 197 kilojoules of energy to be infused into the reaction. So this reaction requires the input of energy, and that's what defines an endothermic reaction. So in theory, if you carried this reaction out in a reaction vessel and you held it in your hands, you would feel the reaction vessel actually get cold, because the energy that would be transferred into this reaction would come from the surroundings. And since you're warm relative to the reaction vessel, the kinetic energy required to input into this reaction would come from you, and so you would feel the reaction vessel cool down, and then heat energy would be transferred from you into the vessel. And so in terms of human perception, it would feel as if the reaction vessel was cold. So we can write this reaction. So in other words, energy is required to drive this reaction. All right, so we can rewrite this reaction a different way, where I'm going to show the energy as a reactant, because in a sense that's what it is. It's required to basically lift the products to a higher potential energy in terms of bonding, by contrast to the reactant, the SO3. Now, we can also show this another way by writing an energy diagram for this. Okay, and the reaction progress is on the horizontal axis, and we'll put the energy here on the vertical axis, and I'll just represent the platform for the reactants arbitrarily. All right, and then we have the kinetics, this energy bump here, which is the energy required to initiate the reaction, and then we'll have a platform for the products that will be at a higher level than where we started with the reactants. And I'll just arbitrarily mark this platform as reactants, and I'll use a P to indicate the products here. The main thing to see is that the products are at a higher energy than the reactants. So if I was to put a dotted line here, it's not exactly, my artwork is not the best in the world, but this would be the energy of the products when they finish. And then if we go like this gap right here is the delta H of this reaction. And you can see that H2 minus H1 is going to be a positive number, because this number right here is bigger than H1. All right, so this is the energy diagram associated with an endothermic reaction. Now, since the delta H for an endothermic reaction can be considered a reactant, right? if we go back and we think about what we've already learned about Le Chatelier's principle, where if we manipulate the concentration of one of these components, we can shift the reaction either left or right, depending on whether we're putting reactants into the reaction or whether we're putting products into the reaction, where the reaction is at equilibrium. So if we treat the energy as if it is a reactant, then we can talk about now what happens if we heat or cool this reaction. So let's consider first off the option of cooling. So if we were to cool this reaction, that would literally have the effect of removing this value. All right, and if we remove this energy, that's the same difference as removing a reactant, and it would have the effect of shifting this reaction to the left. So if we remove energy from this reaction, that has an effect on K of actually reducing the value. So remember, if the K constant represents the ratio of essentially products to reactants, all right, and if we remove the energy here, which causes a shift of this reaction to the left, that in essence, because equilibrium constants are dependent on temperature, essentially what we're doing here when we remove energy from this reaction is we're making the equilibrium constant smaller. And what that means is that the proportion of reactants to products is going to have to be bigger. So to clarify what I just said there, if we remove energy from the reaction, then in essence what we're doing to K is we're shifting that equilibrium proportionality like this, where now the equilibrium reactants are going to be shifted in the direction of being greater than the products. In other words, this value is going to be made smaller. Now, if we want to force a chemical reaction, an endothermic reaction to the right, so that we enhance the amount of products being formed, so in essence we want to make the equilibrium constant larger, then what we need to do is heat the reaction. So what I'm going to do is I'll rewrite the chemical equation here, and we'll go through this little process over again. So in the case where we actually heat the reaction, so we're going to heat an endothermic reaction, all right? In that case, what we're doing is actually pumping energy into the reaction. So if you think back to the early videos that I did on Le Chatelier's principle, where we talked about concentration, heating an endothermic reaction is the same thing as funneling more reactant into this reaction, and what it's going to do is have the effect of shoving the reaction in the direction of the products. So in essence, if we go back to a generalization of the equilibrium constant, so again it's a ratio of products to reactants essentially in a generalized sense, then what we're doing when we heat this reaction is we're actually making the Kc larger. Alright, so the thing about heating and cooling exothermic and endothermic reactions in Le Chatelier's principle that is different than the other aspects of Le Chatelier's, alright, and there were three aspects: concentration and altering pressure by volume changes, and the third thing is altering the temperature, and that's what we're talking about now. The difference between what we're dealing with here and the other two options is that when you heat or cool a reaction that is either exothermic or endothermic, you actually are affecting the equilibrium constant directly. So in terms of an endothermic reaction, you actually are manipulating the K, and you are making it a larger in magnitude number. By the same token, when you cool the reaction, all right, which again, coming back up here to this option, where we're removing the delta H, you're having the effect of actually making this magnitude number smaller. So its final value is going to represent a ratio of reactants to products which is going to be larger than it was before you began cooling the reaction. And in the case of heating, you're going to manipulate that K value, the magnitude of this number, and it is going to be larger as you're going to increase the magnitude of this number as you heat the reaction. So basically what you're doing there, to put a graphic on it, is you're actually increasing this proportion now as you heat it. All right, so the key is, to finish, is that in terms of Le Chatelier's principle and heating or cooling a chemical reaction, if the reaction is exothermic and you want to shift the reaction to the right, you should cool it. And in the case of an endothermic reaction, all right, in the endothermic option, if you want to shift the reaction to the right, then you need to heat it. All right, and with that, I'm going to go ahead and close the video.